Hello, complex analysis students. So today we're going to talk about the Cauchy Integral Formula. This is one of the most central theorems of all the whole subject here. It has some really powerful implications. It's really useful for calculation. Yeah, it's pretty important. So this is sort of our fundamental theorem of calculus here for complex variables. So let's jump into what it says. So the Cauchy Integral Formula theorem says, let f be an analytic function inside and on a simple, closed, positively oriented contour C. And if z0 is some point on the interior of that contour, then the integral around C of f of z over z minus z0 dz turns out to be 2 pi I times f of z0. Another way that this formula is often written is if you solve for f of z0 and write it this way, f of z0 is 1 over 2 pi I, the integral around c of f of z over z minus z0. So if you're interested in the value of the integral, you would use the first formula. And if you're interested in the value of the function, you could use the second formula. The second formula is kind of actually, if you think about it, it's kind of amazing because it's telling us that you can deduce the value of any point inside the contour of, you can deduce the value of the function at any point inside the contour by doing some integral around the outside. So I'd like to go through the proof of this theorem, and then we'll do an example. And what's really cool about this theorem is some of the implications of it. But let's go through a proof of it. Okay, so to start the proof, we want to take a small circle around the point z0 that stays inside the contour. So let's let c sub rho be a positively oriented circle. So modulus z minus z0 equals rho, centered at z0, where rho is sufficiently small so that c sub rho stays inside the original circle C in the statement of the theorem. In the statement of the theorem, C is just some positively oriented contour, a positively oriented closed contour, and F is analytic inside and on it. So one thing that's pretty clear here is that since our C sub rho stays entirely inside of C, where F is analytic, then we know that F is analytic in and on C sub rho. But furthermore, the function that we're trying to integrate in this theorem, f of z over z minus z0, is analytic on C and C sub p, or C sub rho, and the region between them, because the region between C and C rho does not contain the point z0, where that function would have a 0 in the denominator, right? So, little picture over here somewhere. We've got this contour C, and then we've got some point in the interior there that we started with z0, and then we picked a circle centered at z0, positively oriented also, and we called that one C rho, and the radius of its rho. And the region in between here, we know that f of z over z minus z0 is analytic on that region. Now you may remember we had this defamation of paths theorem that says that if the function that you're integrating is analytic on and between those curves like that, then the integral of f, the integral of that function along either contour is the same. So by the deformation of paths theorem, we know that the integral along the contour C, the original contour of f of z over z minus z0 dz, equals the integral around this special curve C sub p of f of z over z minus z0. Okay, so that's important to know. Also, here's a little sort of preliminary fact that I'm going to relegate to a homework problem. If you would integrate around this C sub rho, the function just 1 over z minus z0 dz, it works out to exactly 2 pi I. So I think I will make this a homework problem. It's not a super difficult problem. It involves just using the definition of contour integral. But the idea is basically if you just took the parametrization x of t would be x naught plus cosine t, and y of t equals y naught plus sine of t, where z naught is equal to x naught plus I y naught, and t here ranges between 0 and 2 pi. That's a parameterization of that circle C sub p, or C sub rho. Keep wanting to call it C sub p, but it's C sub rho. So if you took that parameterization and just used the definition of contour integral and just substituted in and worked it out, it works out to 2 pi I. It's not real hard to do. In fact, it's kind of fun because you get to use some trigonometric identities. So work that out and you'll see. But we need to know this fact. And the reason we need to know this fact is that it plays into our sort of game plan. So here's the game plan for doing this proof. What we're going to do is we're going to show that the modulus of the integral around C of f of z over z minus z naught dz minus 2 pi I f of z naught. So we're wanting to show that these two quantities here that we're taking the difference of in modulus, we're wanting to show that they're equal to one another, right? So I'm wanting to show that the thing in yellow there is equal to the thing in blue here. So one way you can show two things are equal is to show that the difference between them is less than any positive quantity. So if the difference between two things in modulus is less than any positive quantity, those two things must be equal. Like basically what we're going to do with the preliminary fact here, 2 pi I, you see 2 pi I right here. I'm going to replace 2 pi I with that integral, then I'll have a difference of integrals that I'm going to smash into one integral, and then we'll be able to get some bounds on it. So let's see how that goes. So now the modulus of the integral around C of f of z over z minus z naught dz minus 2 pi I f of z naught is the same thing as the integral around C of f of z over z minus z naught dz minus f of z naught, and then that 2 pi I I'm going to replace with that integral around C rho of 1 over z minus z naught dz. And like I said, we'll combine that difference of integrals there into one integral. Notice that that f of z naught in front of that integral, you could pull inside the integral because it's a constant. And then I could push that into one integral. Oh, I forgot one thing too. Before I do that, before I smash it into one integral, I want to point out that, remember, because of deformation of paths, that first integral around C is the same as the integral around C rho. So all I did in this step compared to the last step was I replaced the contour C in the previous step with C rho, because we knew that those two integrals were equal by the deformation of paths theorem, as we previously pointed out. So now I can combine this into one integral, and it looks like the integral around C rho, and then the numerator is f of z minus f of z naught over z minus z naught times dz. Okay, now we're cooking. All right, so check it out. We know that our function f is continuous at z naught. So the numerator of that function, we can get an upper bound on it because, with continuous functions, we can get a bound on the difference in the function values if we just choose z sufficiently close to z naught. But our z there lies on that circle C rho, which, we can choose the radius of that circle to be whatever we want, as long as it stays inside the curve C. So here's what I'm going to do. Let's let epsilon be arbitrarily chosen. Let epsilon be greater than 0. Now we know f is analytic at z naught, so that tells me f is continuous at z naught. And because f is continuous, then we know there exists a delta greater than 0, such that anytime z minus z naught is less than delta, that implies that the difference between f of z and f of z naught is less than, I'm going to say, epsilon over 2 pi. It'll be convenient to divide by 2 pi to make something cancel a little bit later, but epsilon over 2 pi here is a positive quantity if epsilon is a positive quantity, so epsilon over 2 pi can serve as the epsilon in the definition of continuity. Now, to make things work, let us choose rho sufficiently small so that C sub rho stays inside C, and I want rho to be less than delta. Okay, so now we're ready for the grand finale. So check it out. The quantity that we had above there, C rho, the integral around C rho of f of z minus f of z naught over z minus z naught dz. So, I want to use that theorem that says that the modulus of the integral is less than or equal to this m times L business, where here the m is is an upper bound on the modulus of the thing that you're taking the integral of, and the L there is the length of your curve. Well, the length of C rho is easy because C rho is a circle of radius rho, so this is just 2 pi rho, right? the thing is, the m that we're going to get, if you look at this fraction here, since we're doing an integral, the z's that we're talking about are actually on the circle C rho. So we know that the distance between z and z naught is just rho, exactly rho. So this is rho. And then the numerator up here, we know we can make that less than epsilon over 2 pi. This is the way that we established the upper bound on the function. So let me write this up a little nicer here. I just want to give you a little scratch work version of it and kind of let you know where we're going with it. So that integral is less than or equal to, okay, the bound on the function is going to be epsilon over 2 pi. So that's the numerator. And then the denominator is exactly equal to rho, so I'll just put rho there, times the length, which is 2 pi rho. And of course, when you multiply all that out, it comes out to epsilon. And let me write my rationale here. Since for z on C rho, we have the modulus of z minus z naught actually equals rho, which we've chosen to be less than delta. So modulus of f of z minus f of z naught is less than epsilon over 2 pi by continuity. So modulus of f of z minus f of z naught over z minus z naught is less than epsilon over 2 pi over rho, since again, modulus z minus z naught is actually identically equal to rho for points on that circle. All right, so check it out. We did what we said we were going to do. We took this difference up here at the top, and we showed that it's less than epsilon, where epsilon was arbitrarily chosen. So thus, this integral c f of z over z minus z naught dz minus 2 pi I f of z naught is less than epsilon for every epsilon greater than 0, which tells us that the integral around c of f of z over z minus z naught dz actually must equal 2 pi I f of z naught. Very cool. Okay, so here's an example of something we could do. Probably we could do this integral from scratch, but I just want to show you how you could use it to calculate how to use Cauchy's integral formula to calculate an integral. Here we're going to do the integral of z divided by 3z plus 2, where c is just the positively oriented unit circle. So what I want to do is make the integrand in this be of the form that you see in the Cauchy integral formula. So I want the denominator to look like z minus z naught for some constant z naught. Well, we can do that pretty easy. Just pull a 3 out of the denominator. So write this as 1/3 integral around c over. So then it would look like z. If I want a minus there, then I'll need to put minus 2/3 here, like so. So now this looks like, in Cauchy's integral formula, it looks like this, right? F of z over z minus z naught dz. So you can see that the numerator of this function is the function z, and it's a very simple function. So this is your f of z from Cauchy's integral formula. And then negative 2/3 here is your z naught. So according to, and by the way, when you think about this function f of z, that function's entire. It's just a really basic polynomial, right? And so certainly our function is analytic on and inside of this unit disk. So I can immediately apply Cauchy's integral formula. So this will be 2 pi I f of our z naught, which is negative 2/3. But our function f is just f of z equals z. So this just equals 2 pi I times negative 2/3, or negative 4/3 pi I. This is a simple one, but most of these problems go kind of like this. We could do another one. For example, I don't know. Let's say I wanted to do integral around the contour c of cosine z over z squared plus 9 dz, where c is the positively oriented circle, absolute z equals 1. So again, just the unit circle, positively oriented. Oh, actually, I wrote this down a little bit wrong. I wanted to do cosine z over z times z squared plus 9. If I wanted to do this integral, now I think this one would truly be a difficult integral to do if you had to write up a parameterization and substitute and do it from scratch. But using Cauchy's integral formula, it's actually pretty simple. Think of this as the integral around c of, okay, put the cosine of z over z squared plus 9 in the numerator like this. So then all that is over z minus 0, just for emphasis, dz. Notice that that function that's in the numerator, the thing that we would think of as f, it's not an entire function. It has two zeros that could happen in the denominator at plus and minus 3i. But plus and minus 3i are not inside or on our circle that we're integrating around. So our function f is definitely analytic inside and on our curve that we're integrating along. And 0 there, the thing you're subtracting off in the denominator, is inside your curve. That's an important part of it too. Got to make note of that. As in the previous example, negative 2/3 was inside our unit disk. I forgot to point that out, but it was true. So anyway, yeah, so we can do the Cauchy integral formula. So this is just 2 pi I times f of 0. 0 is the point you're subtracting off in the denominator, right? So your z naught is equal to 0. And then f of 0 is, well, you plug 0 in there. Cosine of 0 is 1, and then you get 9 in the denominator. So this is 2 pi I times 1/9, or 2/9 pi I. That's pretty fabulous. I mean, it doesn't get any easier than that. Not too much easier anyway. And there's a wonderful extension to the Cauchy integral formula. Has basically the same hypotheses as the original Cauchy integral formula. Your function f has to be analytic inside and on a simple closed contour C that has positive orientation. And you've got to have a point z naught that's on the interior of the curve. This time, you notice in the integral, the z minus z naught term in the denominator there is raised to the n plus first power. Cauchy's integral formula says that this variant of our original type of integral will be equal to 2 pi I over n factorial multiplied times the nth derivative of f at z naught. And this holds for n equal to 1, 2. I guess it actually holds for 0 too. In the case n is equal to 0, it's the original Cauchy's integral formula. And of course, we could write this in a separate form. We could solve for the nth derivative of f at z naught, and then that will be n factorial over 2 pi I times the integral around c of f of z over z minus z naught to the n plus first power. I'm going to skip the verification of the extension, but it's not a terribly long proof that you can look up in the book. It's not overly complicated either. So I'll leave it to you to have a read of that. But let me show you how you would use it just to compute an integral here real fast. Maybe an example or two. Yeah. So let's take a look at this first example here. Now, first of all, you can see that you can write that as, I guess I forgot to say what my curve C here is. What is my curve C? Let's say C is the positively oriented circle, mod z equals 1 again. You can use other curves than the unit circle positively oriented, but it usually doesn't make that big of a difference what curve you use, because you notice when you do this formula, you don't really make reference to the actual parameterization of the curve. In any event, so check it out. So just for emphasis, this is the same as e to the 2z over z minus 0 raised to the 3 plus 1 dz. So I'm trying to make it look just like the extended Cauchy's integral formula up there. So you can see what your function f is. Your function f is e to the 2z, and you can see what your z naught is here. Z naught is equal to 0. So and notice that 0 is inside of the circle that's centered at the origin there. So, and also the function f of z is entire, so it's certainly analytic inside and on our unit circle. So therefore, Cauchy's integral formula applies, and I can use it. And so the integral would be 2 pi I over our n here is equal to 3, so it'd be 3 factorial times the third derivative evaluated at our z naught, which is 0. So off to the side here, we need to calculate the derivatives up to the third derivative of our function. So f is equal to e to the 2z, f prime is 2e to the 2z, f double prime is 4e to the 2z, and f triple prime is 8e to the 2z. So I need to plug 0 into that, and I get 8. So this will be 2 pi I, 3 factorial is 6, times 8. So cancel, there's a 4, there's a 3. So 8/3 pi I, it looks like, if I did my arithmetic correctly. Okay, here's another example. Now this one, we're doing it, it's a little bit different. We have to work a little harder to figure out what our function should be in the numerator and how to set this thing up. But we're going to do the integral around this contour C of 1 divided by the quantity z squared plus 4 all squared. And C is this positively oriented circle, but it's not centered at the origin this time, and it's not the unit circle. So this one's centered at I and has radius 2. So this circle, let me graph it real quick over here. I. So here's my circle, centered at I. And it will be helpful to factor the denominator out a little bit. So z squared plus 4, I could factor that as z plus 2i times z minus 2i. And so the denominator really is z minus 2i quantity squared times z plus 2i quantity squared dz. So notice that we get these two zeros in the denominator, these problem points. One of them is at 2i, and the other one's at negative 2i. So if we want it to match up with Cauchy's integral formula, we want the zero that you're getting in the denominator to appear inside your circle. Now our circle here, I forgot to indicate the orientation on it, but our circle here, C, does contain 2i. So I want the factor z minus 2i squared to be in the denominator because that's the point that's inside. And then the z plus 2i part, I'll need to move up to the numerator. So I'm going to think of this function this way. It's going to be 1 over z plus 2i squared over, and then in the denominator I have z minus 2i, and for emphasis I'm going to write that as to the 1 plus 1. So I can see what my function f is. Here's my f of z, and I can see here that z naught is positive 2i, and I can see what my n value is. N is equal to 1. So according to Cauchy's integral formula, oh, by the way, let's make sure that all the hypotheses of Cauchy's integral formula are satisfied. That function f of z is analytic on the entire plane except for at the one point, negative 2i, which causes it to be 0 in the denominator. But that point, negative 2i, is outside of our circle. So I'm not worried about that problem point. So yeah, f is analytic where it needs to be analytic on the curve and inside of it. And the point 2i, or z naught, is inside the curve C, so that checks out. So the hypotheses are satisfied. So let's do this thing. So according to the extended Cauchy integral formula, this integral will be 2 pi I over n factorial. N is equal to 1 here, so that's just 2 pi I over 1 factorial if you like, just for emphasis. And then we need to multiply that times the first derivative evaluated at our z naught, which is 2i. I get everything there? Yeah. And so just real quickly, if f of z is 1 over, well, our original function f, I'm just going to write it as z plus 2i to the negative 2. So f prime is, just do the power rule, so negative 2 z plus 2i to the negative 3. So f prime evaluated at 2i will be negative 2 times 4i to the negative third power. What does that work out to be? Like, well, we know I would be like negative 2, and then you'd have 64 I cubed in the bottom, so that's positive 2 over 64i, so negative 1 over 32i. So this will be 2 pi I times negative 1 over 32i. And then we get an I times an I, so there's another negative, so the negatives cancel. So it looks like I'm going to get pi I over 16. No, I forgot, I multiplied the I off, so it's just pi over 16. Pi over 16. There we go. So that's how you can use it, just in computation of integrals. A couple of examples. Oh, here's kind of a nice example. So if C is any simple, closed, positively oriented contour, and if we let z naught be any point on the interior of that curve, then the integral around C of 1 over z minus z naught dz is 2 pi I. So this is essentially that homework problem that I gave you earlier where I told you to do the integral around C rho in the proof of the Cauchy integral formula, and then you just apply the deformation of paths theorem. So this integral would also be 2 pi I. So that's just a basic fact. Another way to look at that is you get this immediately from Cauchy's integral formula itself. If you just took the numerator to be the function f, which is 1, then it would be 2 pi times f of z naught, but if the function is just identically 1, f of z naught becomes 1, you just get 2 pi I. And then in the next one here, it just turns out to be 0, because if you apply the extended Cauchy integral formula, this would be 2 pi I over n factorial times the nth derivative evaluated at z naught. But the original function here, again, is just f. I mean, the original function f is just the constant 1. So all of the derivatives of f are equal to 0. So this term right here goes to 0. So if you ever see those two little special integrals, they're quite easy to evaluate, and we get them immediately from the Cauchy integral formulas. Next up, we have several really big facts that are direct consequences of the Cauchy integral formula and its extension. It turns out to be really useful to sort of recast the Cauchy integral formula and the extended version of it here. Instead of the nth derivative at z naught, we think of that z as a variable where that z is in the interior of the curve, okay? And then, so we're kind of like making the variable z, if we want z to be our variable, we're sort of moving that to the place of z naught. And then the variable inside the integral becomes some other, we need to make it some other variable, so we call it s. So here's a nice way to think about the nth derivative of f of z. So now we have a real variable here, where z is any point on the interior of the curve C. So it's just a different way to think about the derivative. And so, of course, we're going to glean a lot of information about differentiability from this formula, because there's a derivative a formula for the derivative that we can work with. So, for example, here is a big result, this theorem right here. It says if you have a function that's analytic at a point, then its derivatives of all orders are analytic at that point. So once you know a function's differentiable at a point, not just differentiable, but analytic at a point, that means it's differentiable at that point and on the neighborhood of that point. And it goes all the way down. All the depths of derivatives that you want to do, you get it. That's pretty cool. In fact, at one point when we were proving the Cauchy-Goursat theorem, I cheated a little bit and I said, hey, I'm going to know a little bit later that at one point in that proof, I wanted to know that the second order partials were continuous, or no, the first order partials were continuous. Well, you get that for free out of this. If things differentiable all the way down, then of course all the partial derivatives that you get from the component functions are, they're continuous at all orders. So that comes from this. And in fact, as I've thought about this proof, it doesn't depend on Cauchy-Goursat at all. So you wouldn't be engaging in any circular reasoning if you went ahead and cited this theorem to get an easier proof of Cauchy-Goursat, which is why I didn't really want to prove the more complicated proof. So anyway, how do we prove this one? Well, let's start with the fact that we know f is analytic. So let's say the point where it's analytic is z naught. Then we know that there exists some epsilon neighborhood of z naught, so that's just this, circular disk centered at z naught, on which f is analytic. Thus, we would know f is analytic in and on the circle, let's say C naught, positively oriented, of course. We'll just take half that radius of the disk on which the function's analytic. So we'll do z minus z naught equals epsilon over 2. So if I know that circle is completely inside the epsilon neighborhood where f is analytic. So f is analytic in and on this circle of half the radius. So now, check it out. We have the extended Cauchy's formula up here that we have this new characterization for in green. So let me just look at the second derivative. So we can apply the Cauchy, extended Cauchy integral formula, and we get f double prime at z equals, what is it? So it's n factorial over 2 pi I. So n factorial would be 2 here. So we just get 1 over pi I, integral around this c naught, f of s over s minus z to the 2 plus 1 ds. Get all that written down right? Yeah. And this is true for every z inside C naught. So what did we just say? We just said that f prime is differentiable on this disk, on this whole neighborhood. Modulus z minus z naught is less than epsilon over 2. So I know that f prime is differentiable on a whole neighborhood of z naught. So that tells me that f prime is analytic at z naught. Well, now we've established f prime is analytic, but we could just apply the same argument to f prime to get that f double prime is analytic. And of course, I think we've opened up some sort of inductive machine here, right? Like we've tipped over the domino. So we know f prime is analytic. The same argument gives you that f double prime is analytic, and et cetera, et cetera. So, and so on. So this proves the theorem that we wanted to prove here. This is a really simple and short proof to prove such a major theorem. Function being analytic at a point means it's analytic all the way down. All the derivatives are analytic at that point. That's pretty amazing. I like it. Okay, here's a corollary. This is actually the thing that we used when we cheated in the proof of the Cauchy-Integral theorem. The corollary is that if you take f and you write it in terms of its component functions, u and v, and you know that f is analytic at the point, whatever point, z equals x plus iy, then both of those functions, u and v, have to have continuous partial derivatives of all orders. So like ux, uy, uxx, uxy, whatever. However many derivatives down you want to go, mixed order partials of all kinds. They're continuous. And the proof of it's pretty straightforward because remember the previous theorem said if f prime is analytic at a point, then so is all of its, f prime is analytic, f double prime is analytic, and so on. Like we know f prime of z is equal to ux plus ivx, which is the same thing. You can write it as uy minus ivy. We just established that f prime is analytic, and we know that analytic implies continuous. So that tells me f prime is continuous, which in turn, we know that anytime a function is continuous, then its component functions are continuous. So we just established here that ux, uy, all these first order partials, vx, vy, are continuous. Well, that was easy. Okay, so there's the first order ones. How about the second order ones? Next, we know f double prime. We know that it's analytic, and so we can compute its derivative by taking the partial with respect to. So basically, you could start from what f prime is and do partials with respect to x. So like uxx plus ivxx. Or you could write that as, if you did it with respect to y, it'd be uxy minus ivxy. Or you could start with the ones like uyx minus ivx. Or you could write that as uyy minus, it should have been a vy there. Hold on a second. This one should have been yx. Oh yeah. And so then this one would, if you did it with respect to y, it'd be uyy plus ivyyy. So there's a way, any of these would give you the second derivative. And we know that the second derivative is analytic. So that tells me f double prime is continuous, which tells me all these second order partials are continuous. And of course, this just keeps on going like this, etc. Okay, you can do the same thing for the third derivatives and so on. So that's cool. That's a fact we used a little earlier that now we see that falls right out of the Cauchy integral formula. So here's another little theorem. It kind of looks familiar. If you let f be continuous on a domain D, and you can establish that every integral around a closed curve of f is equal to 0, then we can conclude from that the function f is analytic. So let's look at a proof. So under these hypotheses, you may remember the theorem about antiderivatives. I wish this book had a better way of naming its theorems, but we had this 3-part theorem about antiderivatives. And this was part C of that, the hypothesis that if f is continuous and all the integrals around closed curves are equal to 0, then that theorem said that this function must have an antiderivative on that domain. So i.e., there exists some function, big F, such that big F prime equals f on D. And because big F prime has a derivative everywhere on D, it's analytic. But we know that if a function is analytic on a domain, then the theorem that we proved just a little bit ago says that all of its derivatives are analytic on that domain. So by the previous theorem, f's derivatives are all analytic on D. So in particular, f is analytic because f is one of the derivatives of big F. So that was easy. So that's a characterization of analyticity on a set. Just all the integrals around closed loops of the function is equal to 0. And lastly, this is kind of interesting. We can put upper bounds on the derivatives. The size of the derivative, we can always establish an upper bound on it. Suppose that your function's analytic inside and on a positively oriented circle centered at z0. Modulus z minus z0 is equal to r. So this is a circle centered at z0 of radius r. If f is analytic inside and on this circle, so that's a closed set if you include the boundary of the circle. We had a theorem a while back that said when a function is continuous even, so we had continuity because of analyticity. We had a theorem that said that the function has to have a maximum value. So let's let m sub r be the maximum value of the modulus of f of z on that c sub r. Then the modulus of the nth derivative at z0 has to be less than or equal to n factorial times m sub r, that upper bound of the modulus of f of z on c sub r, divided by the radius of that circle to the nth power. And so we get this pretty cheaply using the extended Cauchy integral formula. So under these hypotheses that we have here, we know that fn z0 is equal to this integral, well, n factorial over 2 pi I, integral around c sub r, f of z over z minus z0 to the n plus 1 dz. So then the modulus works out like this. So we can pull that n factorial over 2 pi I. But, you know, the modulus of 2 pi I in the denominator is just 2 pi. And then we know that f of z has this upper bound on that circle. So, you know, if we look at the function that we're integrating here, the whole thing, we know that the numerator part, just by hypothesis, is less than or equal to this m sub r. But we know that the denominator part is actually identically equal to r to the n plus 1 because those values of z are on the curve c sub r. So z minus z naught is actually equal to r. And then we know how to compute the length of the curve. So we're using that thing, you know, it's less than or equal to the m times l thing. We're doing that bit. So that just works out to, okay, times m sub r over, to be less than or equal, okay, less than or equal m sub r over r to the n plus 1, and then times the length of that circle, that's 2 pi r. And so, you know, canceling a few things out, you get the stated theorem, n factorial m sub r over r to the n. One of those r's cancel out there. So there you go. Okay, I think I'll stop there. That was a pretty exciting lecture. I really liked it because there was just so much good stuff happening. Yeah, this might be the best lecture of the whole class in terms of just the pure like density of good stuff that happened. So I hope you appreciated it, and we'll get a few other nice consequences coming up very soon. One of them is actually called the fundamental theorem of algebra, and there's another one called Liouville's theorem, which is a big theorem in complex analysis, and then there's another one called the maximum modulus principle that's going to come right out of this. So we've already seen a lot of good stuff happen, but even more good stuff's going to happen very quickly in short order. So, and then having established those big name brand theorems that I just mentioned, we're going to move on to talking about sequences and series. So anyway, this is really cool. I'm going to stop there though. Talk to you again soon. Bye now.